In this lecture, we will see how to use linear algebra to define codes for which we have convenient procedures for encoding and decoding. So linear codes, an MK code over a field K is a linear subspace of F to the M of dimension K. So for example, let G be the matrix defined as follow over the field F equals F2, the field of two elements. Then the code words of G are all the linear combinations of the rows of G, which are the first row, the second row, the sum of those two rows, and of course, in every linear code, the zero vector. So we have here 4 code words, which are all the linear combinations of the matrix G. We will call the generating matrix of our linear code. Now, an important, as we saw in the previous lecture on coding theory, an important parameter of the code is its distance, because it will rule the amount of errors that we can detect and correct. And to find the distance of linear code, we need the notion of Hamming weight. And a Hamming weight is simply the number, the Hamming weight of vector is simply the number of non-zero entries of that vector. And of course, an important property of that is that the Hamming weight of a vector is in fact the distance between that vector, the Hamming distance between that vector and the zero vector. Now, for a linear code, the distance of the linear code is the minimum of the Hamming weights of all non-zero codes in the code words. Now, the proof of that, well, suppose that you have U and V different such that their distance is exactly the distance of the code. Then, because the code is linear, U minus V is in C, and the distance between U and V is by linearity, just the distance between U minus V and 0, which is the weight of U minus V, which has to be at least as large as the minimum of the Hamming weight of all non-zero codes. So we have ourselves one inequality here, which says that the distance of the code has to be greater, at least greater or equal to the minimum of the Hamming weights. Now we can have the opposite inequality by saying that if U is a code word such that it realizes the minimum of the Hamming weights of all code words, then that Hamming weight also is the distance between U and the zero vector, which is the distance between two code words, which has to be greater or equal to the distance of the code. So here we have the two opposite inequalities. So it has to be that the distance of our code is the minimum of all Hamming weights of. So for example, let's look at that the rows, the code generated by the rows of this matrix. Then we have the 4 code words that are 1, 0, 1, 0, 1, 0. Then we have 0, 1, 0, 1, 0, 1. Then the sum, which is the vector of all ones, and the vector of all zeros. Now, instead of having to calculate the distance between each pair of these code words, different code words, which would take to choose 4, then instead of that, all we have to do is to take the Hamming weight of each of the 3 non-zero code words. So here we have a Hamming weight of 3. Here we have a Hamming weight of 3. Here we have a Hamming weight of 6. And this one doesn't count. So here we have that our distance is 3. Now, important properties can be derived from a generating matrix if it has a specific form, which we call the systematic form. So we say it has a systematic form if it's of the shape of an identity block followed by a matrix we'll call P. So here the identity block is K by K, and P of course has to be a K times M minus K matrix. Now it turns out that each code word has a particular form, which you can see. If so, a code word is a linear combination of the rows gi's of the matrix G corresponding to coefficients lambda 1, lambda k, then you see that the first k coefficients of the code word are exactly lambda i's, and we call these the information symbols, while the last ones we can't really predict their form, but they basically are the redundancy. So if we had no redundancy in our code, then all we would transmit would be the vector lambda 1 lambda k, and we would just hope that there is no transmission error. But by having those check symbols, we have redundancy, and we hope that this will enable us to detect and correct errors. Now, another important notion is the notion of a parity check matrix, which we will need for the decoding. So a parity check matrix is a matrix H such that V times H transpose equals 0 is equivalent to V being in the code. Now, it turns out that if G is in systematic form, that is an identity block followed by P, then H being minus P transpose followed by the identity block I minus K is a parity check matrix. Now, we will prove that fact. First of all, each row Gi of G multiplied by H transpose is 0. So we will prove that fact, which will tell us, in fact, that at the very least, a code word being, if V is a code word, then necessarily V times H transpose equals 0. That will not prove right away the equivalence, but it will prove the implication in this direction. Okay, so H transpose has the form minus P followed by an identity block of size n minus k, and the coordinate J of Gi times H transpose is dot product between those two vectors. First, the Gi, so the row of index I of G, which has the one at the index I, okay, and then the column, the column vector which corresponds to the row J. So it's a column vector of H transpose which corresponds to a row of H, which has this form where J is so we have a 1 in the jth coefficient, and so that dot product exactly equals minus Pij, which is basically the only term that survives here, the dot product on the first coordinates, okay, and then plus Pij, which is the only term that survives the dot product with the vector of the canonical base in the second half of the coordinates. So what do we know now? We know that every code word is in the kernel of H transpose, but what is the dimension of that kernel? So that is, we know how to calculate that from the rank nullity theorem. Basically, the null space of H transpose, it has dimension k, and because it does have dimension k, and we already have k independent vectors, the GIs, as a matter of fact, which we know are independent, because the rank of G is k, then we have k independent vectors of the null space of H transpose, which is known to have dimension k, so they have to be a basis, and then V times H transpose equals 0 is equivalent to V being a null space, which is equivalent to V being spanned at the GIs, which is equivalent to V being in the code, which is what we were trying to prove here. So, for example, if G is that matrix, so here we have an identity block of 2, and here we have P, and then H transpose is the identity block here, and here we have we have minus p here, okay, which is equal to p because we always in this class consider that f is equal to f2, which simplifies a lot of things. Now we also need the notion of cosets. Okay, so for C being a linear code and mu being any vector in k to the n, the set of the form mu plus C, which is all the mu plus C for C a code word, is a coset corresponding to mu. Okay, so any member of mu plus C is a coset member of that coset, and one particular coset member of interest is the coset member of smallest Hamming weight, which we call the coset leader. Now, syndromes are vectors that are, so each vector of k to the n has a syndrome which is defined as that vector mu times h transpose, okay? And we will need those syndromes for decoding. Now, there's an important property of these syndromes, which is that for two vectors of k to the n, they are in the same coset if and only if they have the same syndrome. So clearly, a syndrome being 0 is equivalent to the vector being in the code. Now, a syndrome is linear, and it turns out that belonging to the same coset is the same as their difference being in the code. So mu and v belonging in the same coset is equivalent to mu minus v is in the code, which is equivalent to the syndrome of mu minus v being 0, which by linearity of the matrix and vector multiplication, the syndrome of mu minus the syndrome of mu is equal to 0. So these syndromes are equal. Okay, so we have here a very easy characterization, of belonging to the same coset, which will come very handy for what we call syndrome decoding. So to decode the received vector, we need basically to find the element of smallest weight such that the difference between that vector and the element of smallest weight is in the code, which basically boils down to finding the closest code word C from the received vector R. Okay. And we just hope that this gives us what was originally sent through the channel. So mu in particular is the coset leader of R plus C. So here is the procedure we call syndrome decoding. We start by computing all coset leaders with their syndromes as a pre-computation that will be used for every decoding procedure. So you receive an R, calculate its coset, you find the coset leader mu that has the same syndrome as the received vector, and you return R minus mu, which is a code word, and in particular the closest code word to R. So here is an example. Let G be the matrix we previously calculated, and here is the table of all coset leaders. Okay, so the coset leader of syndrome 0, 0 is the vector of all zeros, and then we find that the coset leader of 1, 1 is that vector, and it turns out here we're only looking for 4 coset leaders. So we do not even cover all vectors of weight 1. Okay. That doesn't matter. So we keep this, okay, and suppose we receive the vector as 0, 1, 0, 1. Well, we calculate its syndrome, which is 1, 1, and it turns out that it corresponds to this, and this is the corresponding coset leader. So we find out that mu equals 1, 0, 0, 0 is the coset leader of the coset of R. And we return R minus mu, which is the closest code word in C to the received vector R. Okay, so now we've seen the general strategy for using linear algebra to encode and decode. Now we can push this theory even further by looking at specific linear codes which are Hamming codes. The purpose of a Hamming code is to have distance 3. The point of having distance 3 is that we know we correct only one error, and this makes things a lot simpler. In particular, we can basically skip the whole pre-computation of a table of the syndromes of all the Coset leaders, and we'll see how to do that in a minute. So, well, let's do it. Let's do it now. So we have R, the received word, and H, the parity check matrix. Now here is the thing: if R times H transpose equals 0, then, well, we know that R is a code word, and therefore C, we return C being that code word. Okay. Now, otherwise, because we introduce only one error, R is a code word plus some EI, where EI is the ith vector of the canonical basis, okay? And C, of course, a code word. So we're trying to identify which position we have the error, in which position we have the error. So R times H transpose by linearity, C times H transpose plus EI times H transpose. Now, by the property, the elementary property of H transpose is that C, being a code word, times H transpose equals 0. So we're left with EI times H transpose, which is exactly the ith column of the matrix H. So to decode, the only thing we need to do is to identify which column of H is the vector R times H transpose. We identify the index and we flip the coefficient I, the coefficient of index I in the received vector R, and that gives us a code word under the assumption, of course, that there was only one error. Okay, so in this way we avoid having to calculate the table of syndromes. Now, how do we construct such a Hamming code? Okay, so that, for the previous remark, works for every code of distance 3. But now we're going to want to construct a linear code of distance 3. So here is the procedure. Let n be 2 to the m minus 1, and we build a matrix of size m times n, whose columns are the bit decomposition of the integers from 1 to the m minus 1. Okay, so rather than having a theoretical description, let's just work on an example. So for m equals 3 and n equals 7, here is the matrix M that we produce. Now we want to turn this into a parity check matrix, and the recipe to do that is to reorder the columns of M to have the right block of identity. So we want H to be of the form something and an identity block. Okay, so we're going to move basically this column, and this column to the bottom. Okay, so to the right hand side. Okay, and here is what we get by doing so. And so this, of course, is my minus P transpose, and this is identity, in this case, identity of 3. Okay, and that is my parity check matrix of my code. And remember, knowing the parity check matrix is just the same as knowing the generating matrix in systematic form. Okay, now what's the distance of such a Hamming code? Well, here is the important property, is that the distance of the Hamming code is always 3, no matter what the dimensions are. So here's a proof of that statement. Generating matrix of our code has the form, so identity in block of size k of identity and p. Okay, and each row of p is the bit decomposition of a number that is one of those numbers that were not moved towards the right hand side. So they were the bit decomposition of a number of at least 2 non-zero bits, because we moved all those that had only one 1. Okay, so they all have at least Hamming weight 2 is the moral of the story. So first of all, each row has Hamming weight at least 3. Okay, and in fact, if you take a linear combination of the rows of G, you have that the Hamming weight on this side can only increase, okay, because all the ones, they're all in different positions. They never overlap. So it means that you add 2 rows of G, and you know that the Hamming weight corresponding to the first coordinates is going to increase. So it's going to be 2 if you add 2 rows, or 3 if you add 3 rows. At the same time, the Hamming weight of the part that corresponds to the last columns, well, it can never be 0 when you add only 2 rows, because all these numbers whose bit decompositions are in the rows of P, all these numbers are different. So if these numbers are different, adding 2 of those rows cannot equal 0. So if you add 2 rows of G, you have to get at least a Hamming weight 3. And then if you add more than 2 rows, you may have cancellations on this part, but you will have at least a Hamming weight 3 on the left-hand side of your vector. Okay, so that proves you that you know whatever you do to the rows of G, you will have, unless of course it's a 0 vector, but whatever you do that is not a 0 linear combination, you will have Hamming weight of at least 3, and 3 is also attained. So that proves the distance of the Hamming code is 3. And that concludes our lecture on linear.